Welcome back everyone. In this lecture we will recall the spectral theorem of self-adjoint operators, then we will move to basic representation theory. So, let us recall the definition of self-adjoint operators. So, I am going to write everything in terms of matrices. So, let us start with m by n matrix, n by n matrix over complex numbers A, and it is said to be self-adjoint if A is equal to A star. Note that A star is defined to be the conjugate of A transpose. And what is spectral theorem actually tells us? If you have a self-adjoint operator, then you can always find a unitary matrix U such that U star A is diagonal. Moreover, we can prove that the eigenvalues of A are real. So, let me state it properly. So, let A is n by n matrix which is self-adjoint. So, then there exists a unitary matrix U such that U star A is diagonal. Note that U star is going to be U inverse. So, it means all self-adjoint operators are diagnosable operators. Not only that, moreover, the eigen value of values of A are real. Okay. So, this can be proved by induction on n. So, let us first actually start with proving eigenvalues of self-adjoint operator must be real, and that is just follows from the definition. So, let us see the proof. So, let us start with lambda being eigenvalue of A with an eigenvector with corresponding eigenvector V. So, then we have the following computation. So, we can compute lambda times and the inner product V V. So, now note that this is same as lambda V V, but lambda A V is nothing but lambda V. If we substitute that, we get this is same as A V V, but using the adjoint property we get this equal to A V A star V. So, then this implies lambda the inner product V V is same as, so A star is nothing but the conjugate A transpose conjugate. So, sorry, A star is same as A because A is self-adjoint. So, then this implies lambda V V is nothing but V comma A V, but A V is lambda V. So, this is exactly V lambda V. So, since inner product is skew symmetric, so you get the using the conjugate property you can see that lambda comes out, then this becomes lambda bar V V. Since eigenvector must be non-zero vector, so that implies that the inner product must be non-zero. So, that implies that lambda must be lambda bar by cancelling the inner product V V on both sides. So, that means lambda must be real. So, this is easy checking. So, now what we can do, we can use induction in order to prove the spectral theorem. So, to prove the theorem, it is enough to prove C n has some orthonormal basis B of eigenvectors of A. So, we just prove that there is this orthonormal basis of Cn consisting of eigenvectors of A. So, one can take U to be the matrix whose entries, the columns are given by these elements of B. So, you take U to be the columns they are the elements of B. Okay. It is easy checking. So, now we proceed by induction. So, the case n equal to 1 is trivial. I will leave it to you. Okay. So, now what we can do, like, so we are working over complex numbers, anyway eigenvalues exist. So, we can actually fix one eigenvalue lambda of A. So, once we have this eigenvalue, then the corresponding eigenspace, okay, that is going to be non-zero. Suppose let us say V of lambda is the corresponding eigenspace A minus lambda I. If this is equal to Cn, then there is nothing to prove. Okay. If V lambda is equal to Cn, then there is nothing to prove. Because A becomes the diagonal matrix or the scalar matrix. So, in this case we do not need to worry. So, otherwise this V of lambda is going to be proper non-zero subspace of Cn. So, in this case what we can do, we can look for this the perpendicular of this V lambda. So, this is the perp of V lambda. So, this is by definition consisting of those W in V such that W dash the inner product is 0 for all W dash in V lambda. So, we already proved that the perpendicular perp of V lambda gives a unique choice for the complement of V lambda. So, in particularly we have Cn equal to direct sum of V lambda and V lambda perp. So, now note that the dimension of V lambda, since it is greater than or equal to 1, that would imply that the dimension of V lambda perp is going to be strictly less than the dimension of V. So, now we can restrict our operator A to this V lambda perp, and it is easy to prove that it is still self-adjoint. Now, using induction, so we get a orthonormal basis B dash of V lambda perp. So, this is orthonormal basis consisting of eigenvectors of A restricted to V lambda perp, consisting of eigenvectors of A restricted to V lambda perp. So, now what we can do, we can actually simply put them together. So, you have this B dash, so which is basis for V lambda, and you can also choose a basis, orthonormal basis for, sorry, this is for the perp, this is for the V lambda. Then if you put them together, you get orthonormal basis for capital V. And note that the orthonormal basis of V lambda will be consisting of only eigenvectors corresponding to the eigenvalue lambda, and this is by choice consisting of eigenvectors of A restricted to V lambda pair. So, that implies this one B union B dash consisting of eigenvectors of A defined on capital V. So, this way we get an orthonormal basis for Cn that consisting of eigenvectors for A as required. So, I will leave it you to check this is enough. Okay. So, this way actually we get an operator, unitary operator, because the unitary operator coming from this orthonormal basing, such that this u star A u becomes diagonal. And this theorem is somewhat very important, maybe later, like when we develop representation theory, there I can actually tell you where we are using. Okay. So, this is all I wanted to recall about linear algebra. So, let us actually get to representation theory. So, let me actually first start with somewhat very basic representation theory. So, for that I am not going to specify the algebra. So, I will start with general associative algebra and work with that, and then define basic notions as what is representation, sub-representation, direct sums and so on. So, let me just recall what we mean by an associative algebra. Anyway, we have seen some examples of an associative algebras. So, let us just recall from the examples. Okay. So, note that the endomorphism of V, or if we take the set of all matrices n by n matrices. So, these both are associative algebras. So, what is the meaning of this? So, you have some addition and multiplication, scalar multiplication. With these operations, they become actually vector spaces over complex numbers and equipped with this ring structure, and both these structures are somewhat interrelated. Okay. So, here we have matrix addition, matrix scalar multiplication and matrix product, and here that sum of maps and then composition of the scalar multiplication of maps, and then we have composition of maps. So, here we have composition of maps, and here we have matrix multiplication. So, with respect to these operations, so these respective spaces, they become associative algebras. So, whatever properties these operations satisfies, if we list them all, then we get the abstract definition of associative algebras. So, let me just quickly outline, I am not going to give all the details. An associative algebra, let us denote it by A. So, this is defined over, let us say, complex numbers, we will not change our field. So, this is indeed a vector space to begin with, defined over C. So, that is the first property. So, A is a vector space over C. Let us say the vector addition is plus and dot is the scalar multiplication. So, this is the vector addition and this is the scalar multiplication. And it is just not a vector space, it also equipped with this multiplication, let us call it a round circle, that is defined from A cross A to A and denoted as A B goes to A circle B. So, you have addition scalar multiplication and multiplication of elements of capital A. So, now all these structures they are interconnected. So, with respect to this addition scalar multiplication, it is a vector space. With respect to addition, the same vector addition that you have to use, and multiplication, this A forms a ring, and now all these three structures are interconnected using distributive laws. Okay. They are connected using distributive laws. For example, if you take A plus B circle C, you get A circle C plus B circle C. Similarly, lambda times A B is going to be lambda A circle B and then A circle lambda B and so on. So, I am not going to list all the properties, but these are all the important properties. So, A is a vector space plus A is also ring, and all this addition, scalar multiplication and multiplication, they are interconnected using distributive laws. So, let us see some examples. So, you can take complex numbers. So, this is an algebra over C, and then we can also take the matrices. So, this is also an algebra, and we call this algebra is commutative. Okay. So, A is called commutative plus associative algebra over C if A circle B is same as B circle A for all A, B and C. So, we will actually stop using this circle and so on. The notation is we simply use A B instead of A circle B, and similarly we write lambda A for the scalar multiplication, So, I try to use this lambda mu's for the scalars and A B to denote the algebra element. So, we also assume, we always assume that the unity, which is the multiplicative identity, which is often denoted by 1, is there in capital A. So, the property is A1 is and 1A is always A for A in A. So, this is the property of multiplicative identity. So, it is clear that the set of all matrices, this will form an associative algebra with unity, where matrix addition, scalar multiplication and matrix multiplication will be the respective operations. Identity matrix will be the multiplicative identity in M and C, and the complex numbers, it will form an algebra over itself, and it is a commutative algebra. And if you want something commutative, so we can take, for example, the polynomial algebra generated by one variable x, and more generally we can also take polynomial algebra generated by any n variables. So, that is an associative algebra over complex numbers with unity. So, for us actually the more interesting examples comes from groups. So, we can take G to be a finite group and then consider this CG, which is the set of all maps from G to C. So, this is the set of all maps from G to C, and we have already seen that the vector addition and multiplication on this CG. So, which is defined by pointwise addition and pointwise multiplication. Now, we can define this convolution product on this. So, F star G on x. So, given f comma g in C g. So, define this convolution product f star g of x to be equal to summation f of x f of let us say y and g of z, where y z is given by x. So, now note that we assume that G is finite group. So, this sum is finite, and so this is how we define f star G for all x in G, and this is what called convolution product. And with respect to this product and pointwise addition and pointwise scalar multiplication, this space of functions from G to C valued function from G, that will actually form an associative algebra. So, note that we already had a basis. So, recall delta x is defined to be given by the canonical delta x y. So, that means it is 1 if x equal to y and 0 otherwise. So, now this delta x using the convolution product, it is easy to see that when you take the product, then the group multiplication is reflected among these deltas. So, the delta of x star delta y will be equal to delta x y, and this is true for all x y in G. Okay. So, we can actually have an isomorphic copy of this C G. So, which is defined using the group algebra generated by G. So, this we call it as group algebra generated by G over C. So, how it is defined? So, what we can do, instead of taking the functions from G to C, so we can simply take the free vector space generated by G and then use them in order to define the algebra. So, for example, we can define this E G to be a basis of the vector space. So, this is the basis of C G. So, now using this E G, you define the product E G times E G dash equal to E G G dash. So, now using this, you can actually define addition and multiplication on C G and scalar multiplication as well, okay, because lambda of E G makes sense inside C G. So, as of space, C G is nothing but the linear combination of all these E Gs. So, this is one more way of defining the same group algebra, and one can easily prove that this C G is indeed isomorphic to C power G. Okay, it's a way of actually writing things. So, mostly like we would prefer to use this notation, but sometimes it is also like convenient to use C bracket G and then write things in terms of that. Okay. So, now let us actually define what is a representation of capital A. So, as I said before in the introduction, so representation is all about representing the algebra elements as linear transformation that act on some vector space and use linear algebra in order to understand something about the algebra or the representation space, etc. So, I will demonstrate the representation theory using the finite groups representation theory, but there are some terminologies one can actually define in more generally. So, we will better do it that way. So, let me just define what is representation, sub-representation, etc. So, what is representation of A? So, representation of A, so given element of A you want to represent it as linear transformation acting on a vector space. So, we have this very large space called endomorphism of V. So, this space is indeed a very rich space. We already seen this is indeed an associative algebra over C. So, now if you want to represent an element A as an element acting on a vector space, so what does it mean? So, basically it is an assignment. So, you can think this as a map from A to the endomorphism of V. So, where A goes to rho of A. But of course, the structure that are there involving operations of A, they should be reflected here in the matrix world or the linear transformation world. So, that is why you demand this rho to be an algebra homomorphism, C algebra homomorphism. So, recall, and C algebra homomorphism satisfies the following property. So, this rho must be first of all linear map, because first of all there is a vector space structure on both sides. So, it should be vector space homomorphism, and not only that, it is also an ring homomorphism. So, in particularly rho of AB should be equal to rho A rho B, and this should be true for all AB in capital A. So, basically rho satisfies three conditions. So, the additive condition rho of A plus rho of B is nothing but rho of A plus B, and the second condition which is involving the scalar multiplication rho of lambda A should be equal to lambda of rho of A, and the third condition you can see that. So, this is rho of A B, it should be equal to rho of A rho of B. So, rho preserves all these three operations, and we call that is C algebra homomorphism, and a representation is nothing but a map from A to endomorphism of V. So, usually we call this pair V comma rho as a representation, but sometimes we also use loosely rho as representation, we call rho as representation. The space V is indeed called representation space or A module. So, V is called representation space or simply representation. So, we use all these terminologies interchangeably. Sometimes we call rho as representation, sometimes we call V as representation. So, indeed whenever we say something is representation, it is this pair V comma rho, and of course, this is all representations of capital A. Okay. So, what is sub-representation? A sub-representation is a subspace W of V such that whenever you take rho A which apply on W, then that should preserve W. So, basically W is rho A invariant for all A in A. So, then you call this W as sub-representation. Note that if W is sub-representation, then we can actually have this restriction map. So, from if you have a map rho A defined from V to V, from here we can actually define this rho A restricted to W, which is a map from W to W. So, then we can actually simply define this new representation rho W, which is from A to endomorphism of W, which takes A to this rho A restricted to W. And it is easy to verify if W is a sub representation, then this rho W is indeed a representation of A. So, this is a representation of A on its own. Okay. So, sometimes we use the language of modules. So, this V is called A module. Okay. So, most of the time I will not be using this, I will call everything as representations. Okay. So, we can also talk about the kernel of the representation. So, that is just those elements in A such that rho A equal to 0. So, this is called the kernel of the representation, kernel of representation rho. Okay. As before, one can also define what is called indecomposable representations, but before that let us actually define what is decomposable. So, for that we need the notion of direct sums. So, if we are given two representation, let us say V1, V2. So, these are the two representations of capital A, of course given via rho 1, rho 2. So, then we can define this V1 direct sum V2, that can be defined as representation of A. So, where you define this rho 1 direct sum rho 2, which is a map from A to this endomorphism of V1 direct sum V2, you simply take A and then send it to rho 1 A direct sum rho 2 A. So, that is how given element A acts on this direct sum. So, this is a representation. So, given element A how it acts on V1 direct sum V2. So, this is this new representation, let us call it rho, then this is given by rho 1 of V1 direct sum rho 2 of V2. Okay. So, this is how it acts. So, we will also simplify some notations. So, we write given representation rho from A to endomorphism of V, we simply use AV instead of rho A on V. Okay. So, this is somewhat oversimplified notation, but AV means rho A applied on V. Okay. The action of rho A on V. So, that we can call it like action of A. So, action of A on V. Okay. So, I will stop here and we will continue with basic representation theory in the next class. Thank you.